Now we're going to look at case 3. Case 3 is when you end up having complex conjugate solutions. Let's look at an example of y double prime plus 4y prime plus 7y is equal to 0. My auxiliary equation would be m squared plus 4m plus 7 equals 0. And if I were to try to factor this, there is no combination of 1 and 7, positives or negatives, that are going to get me to 4. So I'm going to use the quadratic formula to find this. So negative b plus or minus square root b squared minus 4ac all over 2a. When I do that, I get negative 4 plus or minus the square root of 16 minus 28 would give me negative 12 inside all over 2. That negative 12 inside my radical means that I'm going to have an imaginary or complex solution to this quadratic. If I wanted to simplify, I would say that's I square root of 12 and then all over 2. And then 12 has factors of 4 and 3. I can take the square root of 4 and get 2i root 3. And then one final simplification here. What that then means is I could write my solution curve as two different things. So e to the negative 2 plus I root 3 x and e negative 2 minus I root 3 x. But we really want these in real solutions, and so Euler has come up with his own formula for his own number. Isn't that quaint and so nice? Okay, he has his own formula for his own number. And what this ends up meaning is you look at your alpha and beta. So alpha in this case is negative 2. Beta in this case is the square root of 3. Any complex number is of the form alpha plus or minus I beta. Okay, so that's where those numbers are coming from. And so we could go through and simplify with some trig and some exponential functions, but this is what ends up being the form. So you have e to the negative alpha x cosine beta x, where that's inside the argument of the trig function, and c2, and then we just switch this to sine. Now, two equations that are really important to know that are expansions of this. Just pull this down here, okay? Are when we have y double prime plus k squared y equals 0. So notice I don't have a y prime term here. And then let's also look at if I have a subtraction, how those are different. All right, so in this case, I'm going to have m squared plus k squared is equal to 0. Well, that means that m squared must be equal to negative k squared, or that m must be equal to plus or minus the square root of negative k squared. Well, we can't, let's make sure we understand that that squared stays with the k because I subtracted that number over to the side. So it would be like 9, like 3 squared, negative 9. Okay, so we can't just be like, oh, well, negative k and then square it. It's more like order of operations. The squared is with the k and then the negative's there. However, we can make this an imaginary number with the negative there and say this is plus or minus ik. What that then tells us is C1, e is then to the 0 x cosine kx, C1 e to the 0 x sine kx. Or you can commit to memory or practice enough and see that something of this form is going to give you the solution curve C1 cosine kx plus C2 sine kx. In one of the problems we did on Tuesday, k squared was 16. And if you look back at those notes, you'll see that the solution curve was C1 cosine 4x, C2 sine 4x. And that's where that comes from. Now let's look at this one here. So m squared minus k squared equals 0. This one's not so tricky because when I add that k squared term over here, I do get that m equals plus or minus k. Or you can think about this as a difference of perfect squares, m minus k, m plus k, and that would give you these solutions as well. This would be distinct real solutions. So one of these is going to be to the positive k, and one of these is going to be to the negative k.